so welcome back. Today it's Friday in my world. I don't know what world you're in, but this is the first one of two here dealing with precipitation reactions and writing out different types of reactions and being able to kind of predict the products. When I mix two different solutions together, how do I know if anything's actually going to happen? And if something does happen, well, what did I just make other than, scary stuff? There's going to be a second part that goes along with this that deals more with the specifics on writing out these reactions. So ionic and net ionic equations comes in the follow-up video to this one. So this is more just about how do I use solubility rules, how do I predict what's happening, what's going on when two solutions are mixed, that kind of thing. And then the second one's, again, a little bit more technical about writing and balancing equations. You'll probably want to have, if you have a handout that has solubility rules on it, or pull one up on the screen. We're going to look at that a little bit later on in this particular video. So here we go. What happens when we combine two solutions together? So a couple things, vocab words to kind of get back in place here. Don't forget, when we're making a solution, we have to have a couple of different components. Number one, we have a solute, which in this case right now is usually a solid that has been dissolved in a solvent, which in this case is water. There can be other types of solvents, but for right now in a Chem 1 class and in a lot of our world, we're going to deal with aqueous solutions. Aqueous solutions are things that have water as the solvent. So yeah, it's possible to have other kinds of solvents out there, but for right now, we're just going to limit our discussion to water-based solvents. So anyway, when you have these two things combined together, we have something called a solution. So we've got to remember that there's always two components to a solution, which is the solute and the solvent. And most of the time when we're doing solutions chemistry, it's really the solute that we're concerned about. The solvent, the water, is kind of in the background. It's there to sort of facilitate the mixture of things, but the water itself usually is not actually a reactant. So you'll see that when we write these equations out, a lot of times the water isn't in there. It's kind of like, well, where did the water go? It's there, and we represent it using the symbol AQ, which means that we've got, say, example, silver nitrate, which is what I have on the board, or this one that's over on the right here is copper sulfate. That AQ means that that water's there. It's dissolved in the water. It's not just the solid form of it. And again, why do we do that? Typically because water reactions are a lot faster. We can see them faster. Solid reactions tend to be really, really slow. Solids do not like to combine with other solids. So there you go. We're going to talk about water-based solutions, aqueous solutions, and we're going to use the letter AQ to represent that a solute has been dissolved in water. So why do we even care about all this stuff? Just as a quick background, don't forget that we're on Earth. Obvious, right? I know. But because we're on Earth, water tends to be an incredibly important part of our chemistry. It's such a dominant, predominant chemical molecule on our planet, and it turns out it's got some seriously weird properties that water does. Water, we only take it for granted because we live in so much of it. But water is a really bizarre compound. But the fact that water can dissolve so many things and that water is so common on our planet, a lot of our chemistry is based in a water background, if you want to think of it that way. So water-based reactions, solutions chemistry, again, happens to be important for us because this is where we live. So again, just why do I have to learn this? Because we're mostly water. So you're mostly water, by the way. So a lot of your biochemistry is also water-based solutions as well. So all right, what do we got? First thing, when we're talking about solutions chemistry, the first step we've got to talk about is that process of making the solution, and remembering that when we put a solute in a solvent, if that solute was an ionic compound, the ions are going to separate. So we have to be able to deal with the concept of dissociation. And you can see on these reactions here, this is what it kind of looks like when we write a chemical equation for dissociation. It's not technically a chemical reaction, it's actually a physical process, but we're going to write it as a chemical equation because it's going to facilitate some of the analysis that we do later on. So when we start off these things, we always start off with the solid form of it. So there's our NaCl, which is our solute, and then it's solid, so we leave it in with a little S after it. And then over here on the right, we can see the AQs, and the AQs indicate now that they're in solution. And when we dissolve an ionic compound like a salt, it turns into its two ions, or the two ions separate. So you've got sodium ions and you've got chloride ions. It's really important to make sure that you write the charges, because the charge is what shows me that it's an ion. And so over here on the right, you've got a picture of kind of like salt. When it's a solid, those ions are touching one another. And as soon as we put water in there, water's trouble, man. It starts to kind of get in between everything and start to separate those ions from each other. So you've got chloride ions sort of surrounded by water molecules. You've got sodium ions also surrounded by water molecules. Water's kind of in and amongst everything. Second thing is, when we do this with slightly more complex formulas like calcium chloride, it's important that when we write our dissociation reactions, they have to be balanced. And every time we separate a calcium chloride molecule, yeah, we get one calcium ion, but don't forget that we get two chloride ions that come out of this because of this 2 that's over here. There's a single molecule of calcium chloride is 1 calcium and 2 chlorine atoms, but when we separate it, we now get 3 different things. In class, I use Legos all the time to demonstrate this, so again, this would be 3 Legos stuck together. We still have to have our 3 Legos separate now here on the right. Keep in mind that this is kind of what it looks like. So if I have a calcium chloride molecule over here, it's actually a molecule doesn't right work, but if they're all dry, over here when we separate it out, there we get 1, 2, 3 different things out. So you have to use subscripts from an ionic formula, a lot of times become coefficients in a dissociation equation. This is similar to how we deal with polyatomic ions. The last ones were binary. Polyatomics work similarly. However, it's really important to recognize that polyatomics stay as a group. The reason why we call them polyatomics is because they have this kind of special stable grouping that they do. They're actually bonded covalently within that group, so they don't come apart when we dissolve them in water. So it's the easiest way to think about it for me, or when I teach students, is to think about dissociating it by name. So this is potassium permanganate, and this really is a picture of potassium permanganate dissociating in water and diffusing through it. It separates into potassiums and permanganates. The permanganate stays as a team. So here's what it looks like when we break it apart. The solid stuff, which is this kind of purple crystal, you can kind of see it down at the bottom down here, and then after time when it separates out, it separates into these 2 things, potassium ions and permanganate ions. It's really important to make sure that you keep the polyatomic together. Don't change the subscript to the polyatomic. A polyatomic team is a team. 1 part manganese, 4 parts oxygen, and overall has a 1- charge. Here's another example for you to try. So this is calcium acetate. So take a second, see if you can figure out what it does. When this thing dissociates in water, what's it going to do? Well, it's going to dissociate into calcium ions and acetate ions. So here's what it looks like. Calcium ions over here on the left, or a calcium ion. And then we have an acetate ion, which is CH3COO or C2H3O2. So there's an acetate ion. We have 2 of them because of this number right here. Again, it's kind of important to make sure that when you're doing these sorts of things to kind of keep in mind the different subscripts. Subscripts that are part of a polyatomic formula stay with that polyatomic. Subscripts like the 2 right here that come from balancing charges become coefficients. So that little 2 there becomes that 2 right there. So again, it's a little bit of a trick. It takes a little bit of practice to remember how that works. Okay, so precipitation reactions. What does this mean? Now that we know all the ions that are getting mixed together, what are the new combinations that can form? And I joke all the time about the high school dance, all right? We came together as friends now. Ooh, who's across oh, potassium, very nice. Chromate, hello chromate. How do these guys come together when they mix? A lot of times, I want you to understand that many times in chemistry, you can mix 2 things together and nothing happens. It's actually super boring. So don't go around like your house and start mixing stuff and hope something's going to explode, or it just doesn't work like that. However, when I'm in a chem class, I'm going to give you things that I know have a pretty decent chance of reacting together so you can see something. It's not like watching paint dry here. Ooh, look what you do. We made white solutions. Cool. So anyway, here's an example of what happens of one case where you can have 2 different solutions come together, like potassium chromate up here, and it's yellow. It's like a really gross, disgusting, bright yellow. And then silver nitrate solution. Silver nitrate solution is what this stuff at the bottom looks like. It's just a clear solution, maybe a slight grayish tinge to it, but it really doesn't look like very much. But when you combine these 2 solutions together, it's like magic. This crazy, bright, reddish, orange, rust-colored stuff just appears almost like magic out of nowhere. We know something's happening here. That's a sign of a reaction, right? 2 signs. We've got a color change, and we have a formation of a solid. So we know that there's a reaction here. This is called a precipitation reaction. When we have something new that's forming, this silver chromate, that's insoluble. It's no longer capable of staying dissolved or separated in water. They come together so strongly that they form these little solid chunks and then fall out. And it looks cloudy to us at first, and then if you let it sit for a little while, the stuff will settle down to the bottom and you get this little kind of muddy, silty looking stuff at the bottom of the test tube. So this is how we start to kind of analyze these reactions and take them apart. How do we know what's going to happen? So we have to look for new combinations of ions. So first thing we have to know which ions came to the party, and then we kind of have to know which the new mix and match that's going to go on here. And are any of those mixes and matches, any of those new combinations, insoluble? In other words, so strongly attracted that they form a solid and fall out of solution. So here's the basic series of steps. Number 1, do your dissociation. figure out which ions are present. Number two, kind of do the switching partners. Well, this came with here, it could go with that one, or this one could meet this one. You kind of do the new ion combinations. Mix and match, it's called double displacement, but figure out the new pairs that could form. And then the third thing is you got to look at your solubility rules to determine if any of these do something interesting. The key that you're looking for is something that's insoluble. Insoluble means it's a precipitate. It's no longer capable of staying dissolved in water, so it's going to form something and then settle out. So here's an example for you to kind of, or that we'll work through. If you have lead 2 chloride and potassium sulfate, will anything happen? And if it does happen, what would it be? So the first step, I'm going to apply step number 1, figure out which ions are present. So here's my 2 chemical formulas, lead 2 chloride and potassium sulfate. Here's when I start to break it apart. I'm kind of exploding it out into the ions. I've got lead ions and 2 chloride ions. I also have some potassium ions and sulfate ions. Again, sulfate stays as a group. What are my new possible combinations? You can either look at it by words or you can look at it with the formulas, whichever happens. I usually go for the outside pair first and then I'll do the inside pair second. So a new possible combo would be lead and sulfate. And the second possible combo would be potassium and chloride. Remember, always write the metal first, the cation first, and then the anion second, even for the inside pair. So here's our 2 possible products, lead 2 sulfate, potassium chloride. And are either one of these interesting? So this is where I have to now pull out my solubility rules and figure out what's going on there. So here's some solubility rules. It's close to the ones that we use in our class, a little bit different, but fairly close. They're all fairly standard like this. So what I'm looking for is anything insoluble. So again, that's the key word here. And I go down kind of from top to bottom and figure out what they are. So my 2 possible products are lead sulfate and potassium chloride. And I literally kind of go down by the rules. So lead sulfate, what's going to happen to that? I kind of go down my rules. Lead sulfate doesn't apply rule 1, doesn't apply rule 2 because it's lead and sulfate, doesn't apply rule 3, but rule number 4 here is about sulfate salts. So it says in here most sulfates are soluble, but there is a notable exception. In other words, except for lead sulfate. Lead sulfate is not soluble, that's why it's an exception. So that's probably our precipitate according to rule 4. And then if you go back and look at potassium chloride, according to rule 2, and again, you start at the top, that rule doesn't apply. This rule right here deals with potassium, so potassium is most likely going to be a soluble one. Again, it's soluble, so that's nothing interesting for us. So our lead 2 sulfates are precipitate. So same thing, here's a couple of example problems for you to practice on. I'm going to have to hit pause here because the bell's about to ring pretty quick for me. So I'm going to have you guys kind of take a look at this. Will a precipitate form, and then if so, what is it? So you've got 2 pairs here, sodium hydroxide and nickel 3 nitrate, and then ammonium phosphate and potassium sulfate. So you guys hit pause, see if you can work it out. I'm going to hit pause as well, and I'll come back a little bit later to finish my video, and you'll see that in part 2 of this video. Okay, well, welcome back. Hopefully you hit pause and you're restarting this. I've magically changed location since the battery in my computer died, so now I'm someplace else. Magic. Anyway, so our job was to hit pause and to take a look at these 2 reactions and try to use the solubility rules to figure out what the precipitates would be and if there is one. So we'll start with this pair over here, sodium hydroxide and nickel 3 nitrate. So first thing, make sure you can write your formulas correctly. So there they are, sodium hydroxide right here. This is nickel 3 nitrate because it's got to have that 3 on the outside. And then the next part is start predicting your products. So predicting your products, again, you can do the kind of the outside inside thing. So the first one would be sodium and nitrate. And again, this would be sodium and nitrate right here. And the second thing would be nickel and hydroxide. So those are your 2 possible new products that could form from this. So there's the formulas for those guys. Again, don't forget when you're writing your formulas to be checking for things like parentheses and all that kind of good stuff. But there they are. Now the next step is to take a look at our solubility rules and try to figure out if any of those can give us some insight into whether or not something is soluble, in other words, in solution, or whether it's insoluble, which means that it would be our precipitate. It's a solid. So with these, first thing, I start at the top and work my way down. That first rule is about nitrate salts, and that's sodium nitrate. So sodium nitrate right there, we can tell from rule number 1, don't have to go any further, that that one is soluble, which means it's going to be dissolved. It'll be in ions. Oh, hello, cat. Welcome. This is Fozzie. He's my guest chemistry cat, as you can tell. He's amazing. Butthead, go away. So our second one is going to be nickel hydroxide. So let's take a look at this. We have to work our way a little further down. Rule number 1 is about nitrate. 2 is about sodium, potassium, etc. That doesn't apply. Rule 3 is about chloride. Doesn't apply. Rule 4, sulfate. Doesn't apply. Rule 5, hydroxide. There we go. That's the one we're looking at. And it says here hydroxide salts are only slightly soluble. And again, that means that for all intents and purposes, not soluble. That's going to be our precipitate. So that right there is going to be our insoluble PPT. That's the one that's going to form our solid. Yep. Oh, I was cheating. So on this one over here, what are we going to do? Again, similar kind of idea. Inside, outside, or outside, inside to figure out what your two new products are. So here is my two compounds, ammonium phosphate and potassium sulfate. Again, this one, I just kind of put this in here to remind you guys about ammonium and having to deal with parentheses and all that kind of stuff. Remember, phosphate's a 3 minus. Ammonium's a 1 plus, and then here's sulfate, which is a 2 minus. Potassium's a 1 plus. So here's our two possible products for this. We can do the outside version of it, and then we do the inside version of it. So our outside version is ammonium sulfate. Here it is right here, ammonium sulfate. Again, sulfate's a 2 minus and ammonium's a 1 plus. That's why we have all those parentheses and subscripts everywhere. And then the second one is going to be potassium and phosphate. So there it is over on the right, K3PO4. So again, we've got to take a look at our rules to look to see if either one of these is producing our precipitate. What do we have going on here? So first one, let's take a look at ammonium sulfate. Rule number 1 does not apply. Rule number 2 doesn't really apply, at least the way it said. Oh wait, it does. Rule number 2 does apply. I should have hit that one first. Rule number 4 also applies. But ammonium cations are in here, so I actually kind of put the wrong one up there. This would mean that it's soluble, so that's probably not going to be a precipitate. That will be ions in solution. And the second one, K3PO4. We're taking a look at these. Which rule applies? Well, it's not number 1 because it's nitrate salts, but rule number 2 again, if we've got potassium in there, that means it's soluble. So in this case, those would be soluble ions as well. This is no reaction. If I took these two different solutions, poured them together, absolutely nothing would occur. Super boring. That's why I don't let you do this in the lab, because really it's just not that very exciting. So there you go, kind of applying that inside-outside rule to try to figure out our double displacement, to figure out our new products, possible products. Number 2, using solubility rules to figure out if anything is going to be insoluble. Insoluble is exciting for us because that means a precipitate actually happened. So there you go, just in summary in terms of what you learned or hopefully learned in this particular video. Number 1 rule is that when we've got ionic compounds, that they dissociate in water. In other words, they turn back into their component ions, and writing those out can sometimes be a pain in the butt, but if it's soluble, it's aqueous, it's going to be in its ion form. Second thing is when we're combining two solutions together, we're going to do that new inside-outside. It's called double displacement, but we're going to look for those new combinations of ions. It has to be a new positive and negative ion together. Two positive ions will not attract to each other. Two negative ions won't either. So that's why that kind of trick of using the outside and then the inside kind of helps shortcut that particular process. And then the third thing that you do with precipitation reactions is to find a set of solubility rules and then start at the top down. You always apply the rules from top down. The first rule that says something about your compound, that's the rule that applies. Every once in a while you'll see something where two rules will kind of contradict one another. You go with the top rule. Whatever the top rule is, that's the one that wins. And then with this, sometimes there's a reaction, sometimes there isn't. If there's something insoluble, or slightly soluble, I guess is the word they use, that means a precipitate forms and a reaction occurs. If everything on your list is soluble, that means there's no precipitate, and overall, no reaction. Pretty boring to look at, but sometimes kind of nice because you don't have to write as many equations, right? All right. So there you go. Thanks for tuning back into part 2 here in my new environment, and my cat. Hope you liked him. And I'll see you guys next time.